British engineer Barnes Wallis had found a revolutionary way of making a frame light and strong. It looks more holes than metal, and the secret was in the way he arranged the material. It's not about the amount of metal you use, but how you use it. I've devised an experiment at my workshop to show how, with steel, less can be more.
OK, if we're ready, let's try and get it down, but let's get it between the bars.
I don't get just anyone to be my technical advisor. Martin Manning was the chief structural engineer at Hong Kong International Airport.
OK, can we get down?
First, we're going to load up a standard I-beam used in buildings all over the world with 2.5 ton in weight, about the same as 2 family cars.
So, here we go.
As the chain slackens, the beam takes the full load.
You see it bending now.
Yes, I can see the bend.
This 130-kilo beam is holding up. Just. What happens when we increase the weight to 3.5 tons?
Oh, here we go.
So, let's slacken her off and have a look.
Take the load off the crane.
So when the chains start to go slack... Oh,
there she goes.
My word, that is not liking it at all.
Don't take it any further.
That's failed, isn't it? That's broken.
That is seriously broken.
That never even got near it.
The steel beam fails completely at 3.5 tons. You could give this beam more muscle by bulking up, but that would also make it heavier, and they didn't want that at Hong Kong. Amazingly, we can send the I-beam on a diet and still make it stronger. Think Wellington bomber. The answer lies in simple geometry.
So there are things you can do with just the same amount of material, the same weight, but organised in a different way, in a different shape, a different form.
Absolutely.
And that's what we're going to do next.
Yep.
We better tidy this up. That beam's really ruined.
Broken.
Spoiled.
We're in trouble now, I think.
Taking a cue from Barnes Wallis's Wellington design, I've reorganised the steel into a series of triangles. This lattice beam weighs almost 20 kilos less than the I-beam, yet it should be stronger, if the maths is right. The load is spread through the lattice, so it won't bend, or so Martin tells me.
And you think this will be stronger? Yeah. Just because of the shape, the arrangement?
I'm going to test Martin's confidence and load it with a much heavier weight.
Right, let's have the lot on. All of it.
We're loading up every slab we can find. That's 4.5 tons, a ton more than the I-beam could hold.
All the way back.
Remember, this lattice weighs less than the I-beam.
Okay, settling.
It's down.
So, if we watch it slacken off, now at this point, the I-beam just folded. Look at that.
That's not moved at all. There we are.
No.
That's 4 tons of concrete and half ton of steel.
And that's now happily supporting, what, 4.5 tons? And it's not even... that's content.
Yeah, that's quite content. The other one easily failed at 3.5. So say it was safe at 2.75, say. So it's nearly twice the load.
And it couldn't be any clearer, could it?
So that shows how you arrange the steel makes a huge difference to the strength. Our lattice was composed of very strong triangles, just like the Wellington bomber. And a curved lattice of steel, also made of triangles, was exactly what the engineers needed to span the terminal roof in Hong Kong.